Chapter 6. Legendre transformation and the Hamiltonian. Let's start with the Lagrangian and perform a Legendre transformation to get the Hamiltonian formulation. See the next equation. Substituting the relation for generalized momenta, P sub I equals the fraction with numerator partial differential L and denominator partial differential Q sub I, and Lagrange's equations. F sub I equals P sub I equals the fraction with numerator partial differential L and denominator partial differential Q sub I. See the equation shown. Regrouping, we arrive at the Hamiltonian of the system, seen earlier as the energy if the system is conserved.
See equation 6-1, which indicates that P sub I equals negative the fraction with numerator partial differential H and denominator partial differential Q sub I, and Q sub I equals the fraction with numerator partial differential H and denominator partial differential P sub I. Now consider the total time derivative of the Hamiltonian. See equation 6-2. And if H not explicitly time-dependent, we get dH over dt equals 0, thus H equals E, for constant E, the conserved energy of the system. 6.1 Area conserving mappings. Let's consider infinitesimal motion of an object in terms of the generalized coordinates going from q sub 0 p sub 0 to q sub 1 p sub 1 in phase space.
See the next equation. Viewed as a coordinate transformation, the Jacobian is, see equation 6-3. As the infinitesimal is taken to 0, we see that any flow satisfying Hamilton's equations is area-preserving, Jacobian equals 1. The converse is true as well, if the flow an enclosed region under the phase space mapping or flow is area-preserving, then the flow satisfies Hamilton's equations.
6.2 Hamiltonians and phase maps. Since the Hamiltonian is conserved, it involves motion in phase space along curves of constant h equals e. The phase diagram for a Hamiltonian system, thus, consists of contours of constant h, like a contour map. Previously. See equation 6-4. Using. See equation 6-5. Now have. See equation 6-6.
The contours or level curves of the Hamiltonian are invariant sets, as are fixed points. Fixed points in the phase space occur when the gradient of the Hamiltonian is 0. Nabla h equals 0, i.e. partial differential h of slash partial differential q equals 0 and partial differential h of slash partial differential p equals 0. The system is at equilibrium when at a fixed point, so identifying these points, and related attractors and limit cycles, will thus be of interest in understanding a system's dynamics and asymptotic behavior, all to be discussed. Cases 1 to 6 in what follows describe instances of ordinary differential equations, ODEs, with stability as indicated. A complete analysis along these lines locally reveals the various types of stability and general criteria and is discussed in the section after this. If a fully global separability can be obtained, it is clearest in the Hamiltonian Jacobi formalism, also discussed in a later section. Let's start with an analysis of second-order autonomous systems along the lines of. This covers many systems of interest, as well as the linearized local approximation for any system. We begin by describing the system via a real vector, bold italic R of t with 2n components if there are n degrees of freedom, with an associated phase velocity bold italic R of t equals bold italic v of t, which is a first-order vector differential equation. The order is defined as the minimum number of coupled first-order equations, here 2n.
The motions of a second-order system can be described in terms of the flow lines, and fixed points, if any, in their associated the set bold italic R of t bold italic v of t, phase portrait, or phase diagram. This allows a qualitative analysis of the properties of a system, where the special cases analyzed in cases 1 to 6 provide an understanding of the building blocks in such a qualitative analysis. Following, let's first consider phase space maps for special, lowest order Q, U of Q cases, then describe a general class of potentials arrived at by construction from those special cases. To begin, consider U of Q equals AQ. Example 6.1. Case I, U of Q equals AQ. The uniform force field. AQ equals E minus the fraction with numerator p squared and denominator 2m. Recall that p sub I equals negative the fraction with numerator partial differential h and denominator partial differential q sub I, and q sub I equals the fraction with numerator partial differential h and denominator partial differential p sub I, and suppose p equals 0 at t sub 0 and q sub 0. See the equation shown. Integrating the first-order equations.
See the next equation. Exercise 6.1. Show the phase space map for Hamiltonian with potential U of Q equals AQ, and graph of potential. Show that there are no fixed points. Example 6.2. Case 2. U of Q equals positive 1/2 AQ squared. The linear oscillator. 1/2 AQ squared plus the fraction with numerator p squared and denominator 2m equals e, circles/ellipses in phase space. See the equation shown. The second-order equation of motion that results is. See the next equation.
This is classic simple harmonic motion with period t equals 2 pi divided by omega and e equals 1/2 ma squared omega squared. Exercise 6.2. Show the phase space map for Hamiltonian with potential U of Q equals positive 1/2 AQ squared, along with graph of potential. Show that the level curves are ellipses and that there is an elliptic fixed point at Q equals 0, P equals 0. Example 6.3. Case 3. U of Q equals negative 1/2 AQ squared. The linear repulsive force, quadratic potential barrier. See the equation shown. The second-order equation of motion that results is. See the next equation.
So far we've seen a case with no fixed point, an elliptic fixed point, and a hyperbolic fixed point. These are some of the main categories of interest, but to be complete, let's consider a system described by a vector function of time r of t equals q of t p of t, that satisfies a first-order vector differential equation of motion. See the equation shown. A point, qp, where v of qpt equals 0 is known as a fixed point. It represents the system in equilibrium. If as t vector infinity we have r of t vector r sub 0, then r sub 0 is called an attractor. A strong attractor occurs when a phase trajectory anywhere in some neighborhood of the attractor point r sub 0 results in the trajectory joining, asymptoting to, the attractor. Separation of variables is generally possible, from the theory of ordinary differential equations and stability, and will be used to categorize the types of flows, with or without stable points, in the remainder of this section along the lines of. Further discussion of separability occurs in a later section where the Hamilton-Jacobi equation is discussed.
Exercise 6.3. Show the phase space map for Hamiltonian with potential U of Q equals negative 1/2 AQ squared. Show the level curves are hyperbolas, or straight lines if degenerate case. Show the separatrix. Show there is a fixed point at p equals 0, q equals 0, hyperbolic and clearly unstable. Example 6.4. Case 4. U of Q equals cubic. The cubic potential barrier, phase space solution constructed from cases 1 to 3. Exercise 6.4. Show the phase space map for Hamiltonian with potential U of Q equals cubic, along with plot of potential. Example 6.5. Consider the Hamiltonian. H equals A times the absolute value of P plus B times the absolute value of Q. Describe all of the consistent solutions. First case, A is greater than 0, B is greater than 0. Quadrants, I, H sub I equals AP plus BQ2, H sub I equals AP minus BQ3, H sub I equals AP minus BQ4, H sub IV equals AP plus BQ. To get the dynamics, use Hamilton's equations. Consider quadrant I. Q equals AP equals negative B, thus Q equals AT plus A sub 0, P equals negative BT plus B sub 0. So, Q equals AT, P equals negative BT plus H over A. This gives the flow. Second case, A is less than 0, B is less than 0.
Quadrants. H sub I equals negative AP minus BQ, H sub I equals negative AP plus BQ, H sub I equals AP plus BQ, H sub IV equals AP minus BQ. H is less than or equal to 0 is the only consistent solution to A is less than 0, B is less than 0. Third case, A is greater than 0, B is less than 0. H sub I equals AP minus BQ dP over dQ equals B over AQ equals 0, P equals H over A, H sub I equals AP plus BQQ equals AP equals BH sub III equals negative AP plus BQQ equals ATP equals BT plus H over AH sub IV equals AP plus BQQ equals negative AP equals negative B vector Q equals negative ATP equals negative BT minus H over A. Fourth case. A is less than 0, B is greater than 0.
H sub I equals negative AP plus BQP equals 0, Q equals H over BH sub I equals negative AP minus BQQ equals AP equals negative BH sub I equals AP minus BQQ equals AT plus A sub 0 P equals BT plus B sub 0, where A sub 0 equals 0 times B sub 0 equals H over BH sub IV equals AP plus BQ. Similar. Exercise 6.5. What happens at 0, 0? Example 6.6. Consider potential for 1D motion with V equals negative AX to the fourth power A is greater than 0. See the next equation.
There is one fixed point at the origin, x equals p sub x equals 0, and the energy contours consist of the parabolas p sub x equals plus or minus the square root of 2max squared through that fixed point. The separatrix is the unstable trajectory that goes through an unstable fixed point. See the equation shown. Thus, the motion terminates. Exercise 6.6. What happens when SQN of P sub 0 x sub 0 equals 1 ? Show the potential and phase plots.